So, revision chapters 2 to 4. Okay. So, chapter 2 covered the basics of single degree of freedom systems. Okay. So, a lot of it should have been not new to you. But essentially, the main part of chapter 4 is we defined 4 equations. Okay. There were 2 equations to do with undamped systems. There was free oscillation and forced oscillation. Okay. These are the solutions to the equation for an undamped system. So you've got mx double dot plus kx. That if that was equal to 0, you have a free oscillation, and that's the solution to that equation. And then if you've got a force there, then obviously this is the solution. The big difference between the free and forced oscillation is that if you've got a free oscillation, your amplitude A and your phase angle phi are going to be defined by the characteristics of the system and your initial conditions. Okay, initial conditions being the key part there. Here with forced oscillation, this is completely defined by the system and the force being applied. Okay, and notice omega naught is your natural frequency and omega is the forced frequency. So it's the frequency of your choosing that you're forcing the system with. Okay, it's not natural system. It's not the natural frequency. So there are 2 of them. We also defined 2 equations to do with damped systems. So this time you've got mx double dot plus cx dot, which is your damping constant, multiplied by the velocity, plus kx equal, if you've got 0, then you have free oscillation. Okay, so again you've got an amplitude here that's going to be defined by your initial conditions, and a phase angle here called alpha, also defined by your initial conditions. And notice we've got a decaying exponential in there, which is to do with the system, and like I said, to do with the damping. There's your damping ratio. And obviously that means that the oscillation that you have to start with will decay over time. And if that equation doesn't equal 0, if that's some forcing function, then you have this as your solution. Okay, and again, A and delta, which is the amplitude and the phase, are completely defined by the force that's being applied and your system and the characteristics of the system. Okay, it doesn't care what's happening in initial conditions for this equation. A and delta will be defined by the characteristics of the system and the force that's being applied. Okay. And so in a bit more detail, if you've got, this is a free oscillation for an undamped system. Okay, there's the equation of motion. The solution you can write in this form, but this can also be written as a cosine plus a sine term. Okay, we've got a cosine term plus a sine term. We went through the derivation of how do you get from this to this. Okay, you can quite clearly do that. And basically A1 and A2, A1 is a cosine of phi, okay, and A2 is a minus a sine of phi. Okay, and if you go through the motions, you'll end up getting the same problem. Omega naught, which is your natural frequency, is root k upon m. Okay, if you go through sticking this into this equation, you'll end up finding that this will solve it so long as omega naught is root k upon m. Okay, and like I said, all of these variables, these arbitrary variables, a1, a2, a and phi, are defined by your initial conditions. If you know your initial conditions, okay, then you can use this shortcut to get the equation of motion. Okay, so here we've got our our displacement at time equals 0. Here's our velocity at time equals 0, and obviously that's your natural frequency. And you just plug the numbers in, and out will pop a solution. That may not be in the form that we're asked for, but obviously knowing this stuff, you can go from this solution to this solution if you wanted to. If you've got a force system, then this is your equation of motion. This is for a sinusoidal force. And if I'm looking for the steady state solution, so I'm not looking for the transient stuff, then this will be your exact solution, solution for this equation. Okay, and this, notice that here F naught will be known because that's your force that you've got, and K and M are characteristics of the system, and that will be the frequency of the forcing function, omega. It's not omega naught. If you've got damping ratio is defined as the actual damping constant divided by what you get for critical damping. And so you can solve that by knowing, if you know what M and K okay, and you know your C, then you can work out your damping ratio. And your damped natural frequency, so if you've got a damped system, you set it oscillating, that oscillation will decay, but it will oscillate at a certain frequency, and that frequency is related to the natural frequency of the system, the undamped natural frequency, but you've got a 1 minus zeta squared, square rooted, times that. And obviously if zeta is less than 1, which it will be for an underdamped system, then obviously this term is going to be less than 1. So the damped natural frequency will always tend to be less than your undamped natural frequency. Loss angle, which you would have come across on some of the questions that you did for chapter 8, is defined as delta, okay, and you can relate zeta with delta using this equation, and zeta and C using this equation, okay. If you've got a system where there's no forced oscillation, then that term just becomes 1. You don't worry about that term there. So if you've got an undamped system, then zeta is 1/2 tangent of delta. And if you've got a system that's damped, then it's going to decay in terms of oscillation. Well, to work out the ratio of the peaks of the oscillation, you can use this equation, okay, which is to do with the logarithmic decrement, okay, which is lambda, and lambda over here is defined, and you can see that. These equations are on the equation sheet. You don't need to worry about having to write the stuff down. So if you've got damping, you've got a free oscillation. So this is your equation of motion, okay, equals 0. So it's defined as free oscillation. You can write it like this, which is what I showed before, or in terms of cosine and sine terms over there. Again, A1 and A2 are the same thing this time. And again, all those arbitrary variables, A, phi, A1 and A2, are going to be determined from your initial conditions. And if you know your initial conditions, you can just plug it into this equation, and that will give you your solution again. So again, you've got your displacement at time equals 0, your velocity at time equals 0, your displacement at time equals 0, and everything else is defined by the characteristics of the system. So you just plug those things in. Again, all on your equation sheet. If you've got a forced damped system with a sinusoidal forcing function, as I said, your solution looks like this, where A is this term, okay? R is omega divided by omega naught. It's your frequency ratio. F naught you should know, because obviously you've got a forcing function up there. And obviously everything else is defined by the system. K and zeta will be defined by the system. And omega naught, obviously you'll have to work that out too. And so you've got A here and delta over here. And over here we've got a picture of what happens as the frequency goes up of your force system, okay? And what we've got here, M, is our amplitude ratio, okay? So this is the amplitude A divided by F naught upon K. F naught upon K is known as your static displacement, okay? If there is no oscillation, you just applied that F naught, okay? The thing's going to move. It's just going to move by the distance defined by your spring's constant, okay? X dot is 0, X double dot is 0. So you have F naught equals Kx. X is your amplitude, okay? So you end up with your static displacement over here, okay? And then obviously as the frequency goes up, your amplitude will increase up to a peak if you've got damping. If there's no damping, this shoots up to infinity, okay? That's the whole thing about resonance and resonant frequencies. You want to avoid them because your amplitude just goes through the roof. Obviously, depending on how much damping you've got, this peak will be at different values, okay? So something with less damping, the peak will be higher, and something with a lot of damping, the peak will be very low, okay? And then obviously as you go past your natural frequency in terms of driving frequency, then the amplitude will tail off and will end up going down to 0 if the frequency is high enough. Okay. With your phase angle, you start off, okay, the thing will respond in exactly the same together. As you increase the frequency, you get to at the natural frequency, the thing is going to be 90 degrees out of phase, okay, pi by 2. And then obviously as you go beyond this point, it's going to approach completely out of phase, okay? And that's giving you the phase angle. And again, if you had no damping, this, like I said, would shoot up to infinity, and this would be instantaneous. From 0 to 1, you'd have something that's in phase with you, and then from 1 onwards, you'd have out of phase. So this switch would be instantaneous. So that was chapter 2, okay? Those equations that I showed you, okay, are all on your equation sheet. Okay, I haven't got that picture on the equation sheet, but you can, I think I've just certainly described this stuff. And the equation sheet is at the back of your notes. The only thing that I've added on the equation sheet is the way to go from, say, this equation back to this equation. You can obviously you can use Pythagoras' theorem to find a from a1 and a2, and you can use tangent to find alpha from a1 and a2. So chapter 3 was about forced oscillation and looking at the complete solution. Okay, so not just what happens as time goes to infinity, the steady state solution. We're looking at the complete solution, including the transient, and that was made up of what's known as the complementary function and the particular integral. Okay, the complementary function was simply the solution for the free oscillation. Okay, so you can refer back to what we covered in chapter 2, and basically it's a solution to that equation of motion. If with an undamped system, you've got mx double dot plus kx equals 0. That solution, okay, a cosine of omega naught t plus phi was your complementary function for an undamped system. Obviously, if you've got a damped system, then your complementary function will include that decaying exponential. But it's the free oscillation, okay, so when the force is 0. But then the particular integral is what you have, and that's dependent upon the forcing function, okay. And what you do is you take a trial function, and that trial function will always be in the same form as the force that's being applied. So if your force is a constant force, then you take a trial function of a constant. Okay, and if you have a sinusoidal force, then your trial function will be a sinusoid, and so on and so forth. Okay, linear increasing force, it's what you have is you have a polynomial. Okay, with a linear, obviously it's going to be t to the power of 1. If you've got a quadratic, then obviously you've got t to the power 2 and all that sort of stuff. So you take your trial function, that will be in the same form as the force that's being applied. Okay, there is a table in your notes. That table is not reproduced. Okay, so it's worth having a look at it. But like I said, if I've given you the force, you've more or less got the solution that you're going to try. And then what you do is, you attach some unknown coefficients to that trial function, and you solve to find what those unknown coefficients are. And again, that depends on the force that's being applied. You can work out what those unknown coefficients are, and that will give you the general solution. Okay, you add that to the complementary function, that will be the general solution. The thing is there are a couple of arbitrary variables in the complementary function. Okay, a1, a2, or a and phi. Okay, you don't know what they are. As we said, they're defined by initial conditions. So to find the exact solution is you have your general solution, which is complementary function plus the particular integral. Okay, you then have to apply initial conditions to get your exact solution for that specific case. Okay, exact solution depends on initial conditions. So you then apply your initial conditions to your general solution, and you'll get values for the arbitrary variables that you don't know what they are. Okay. Now on your formula sheet, I've given you the general solutions for undamped and damped, for rectangular step forcing function, linear increasing forcing function, an exponentially decaying force, or sinusoidal excitation. Okay, you've got the general solution for both the damped and the undamped cases. Okay, this is on your equation sheet. So if you're sure that the general solution applies to the specific case you're looking at, then you can look at the equation sheet. Okay. For the damped case, okay, sorry, for the undamped case, I've also given you the exact solution if your initial conditions are rest conditions. Okay, so if you know that x of 0 is 0 and x dot of 0 is 0, then I've also given you that exact solution. If those initial conditions aren't 0, aren't rest conditions, then you'll have to go from the general solution, apply the initial conditions to find your variables. Okay, and I've not given the equations for the exact equations for the damped case. Again, that'll be something you have to work out yourself. So that was chapter 3. Chapter 4 was all to do with Fourier analysis. Okay. And the first part was talking about periodic forcing functions or periodic functions, and for that we use Fourier series to solve. Okay. Now here's the equation for Fourier series for general period t. Okay. This shouldn't be new to you. You did Fourier series in maths either last year or the year before last. Okay. But basically this series of sines and cosines, this sum, will end up forming the periodic function that you're trying to represent, be that a sawtooth, a square wave, or whatever. Okay. And you can go through and you can solve for an and bn, which are the coefficients over here, depending on whether the function's even or odd. You can discount one of them. Often, if the function is neither or odd, then you know you've got both of those sine and cosine terms, and you go through solving these integrals. Okay, and you find an and bn and plug them in, and you end up getting your forcing function. Like I said, I'm not going to ask you to solve the Fourier series in this module. Okay, it's not what I'm testing you on. You may find that in the past paper I have done. Don't worry, I'm not going to ask you this year to solve the Fourier series. So like I said, there's a step-by-step process for this one. Okay, the first step is obtaining the Fourier series, and I'm not normally going to require you to do that. But step 2 is where you have to solve each of those Fourier series for each harmonic. Okay, now like I said, what you can do is you can solve it for the general harmonic n, okay, and that will give you a solution for f of n. And then to find your complete solution, you basically add up all these solutions together. And so you end up with a sum of all your individual solutions to get your complete solution xt. Okay, so you take one specific harmonic or the nth harmonic for your solution, you solve it, okay, using the process we used in chapter 3 and chapter 2 to give you an x, and then obviously down here you add up all your x's to get your complete solution. Now we also touched on frequency spectrum, okay, Fourier transforms. And there's two ways of representing functions. You can represent them in the time domain, okay, so that's where you've got a function in terms of time there, f of t, and that's where if you were to plot it, your x-axis will be in time. So you have time equals 0, and as you move on, you'll get different values of whatever your function is. Now the other way to represent that is to look at what's known as the frequency domain, okay, which is in a function of frequency. So you start out with frequency equals 0, and that will increase in terms of radians per second or hertz. And basically the frequency domain will show the magnitude of the strength of each individual frequency that go into making up your signal. Okay, gives us strengths of various frequencies that contribute to make up a time domain signal. Now we did this transformation with the Fourier series stuff. Okay, your coefficients an and bn will be the magnitude of the sine or the cosine of a certain frequency that go up to make up your time domain signal. Okay, so if your time domain signal is a square wave or whatever, you've got an an or a bn term. Okay, then you can go in and you can make up, you can plot your frequencies, okay, along the bottom, and you can have your values for an and bn at the certain discrete frequencies that you're using, and that will be a frequency domain spectrum. But the thing is, with Fourier transforms, that was only one type of Fourier transform. Fourier transforms can be applied to all sorts of other types of signal, okay? Things like random signals and stuff, and you can get the frequency spectrum for that time domain signal. Like I said, I've not covered the maths, and again, if you look at your previous exams, sometimes I've asked you to sketch the Fourier transform of a certain function, okay? I'm not going to ask you to sketch the Fourier transform of functions this year, okay? That's one of the things that was removed from the content when this was merged with the control systems engineering module to become this dynamics and control. Okay, I had to drop some of the content. We went from 20 credits to 15 credits, and that was one of the things I dropped. I'm not focusing on the maths of Fourier transforms and you having to sketch them. If you're interested, chapter 9 contains some of the maths. Like I said, Fourier transform can be used with a variety of signals. Okay, we've already done one type, periodic functions. Okay, but it can also be used for random vibration, non-periodic signals, and discrete signals using what's known as a discrete Fourier transform. Okay, This is sort of measurement, instrumentation stuff. And the DFT is discrete Fourier transform. The one that you'll come across most frequently in engineering will probably be known as the fast Fourier transform. And that's a specific type of Fourier transform that you can use on the computer. Okay, and it's particularly efficient in the way it solves it. And a typical example would be you have a component that you developed as part of your industry or whatever, okay, and that component is possibly going to be subject to some periodic excitation, okay. An example would be, say, I don't know, a helicopter, okay, part of the helicopter, obviously that's going to be subject to some vibration because of the rotors and stuff, but what you want to make sure is that your component is going to be able to deal with that oscillation, okay, and you don't want it to hit resonance. So what you do is you take your component, you shake it with a random vibration. That will give you a time domain result, okay, of the accelerations felt by that thing. And what you can do is you can pass that through your Fourier transform, and that will give you a frequency spectrum. And the peaks of the frequency spectrum will be the fundamental frequencies of that component, okay. So if you didn't work it out analytically, because it's not a nice natural thing like a spring and a mass, okay, it's some other sort of component, some structural component or something, okay. Like I said, you can shake it randomly and it will get a time domain result. Take the Fourier transform of that, you get your natural frequencies. And what you want to do is make sure your natural frequencies don't coincide with the oscillation that's being excited, okay. So like I said, with the helicopter example, you want to make sure the natural frequencies of that structure won't be excited by the oscillation of the rotors. So here's another example of the Fourier transform. Here's my time domain signal, okay. Well, this is actually time, but sample number, but with a certain number of samples per second. That's your sampling rate, okay. Then you've got an amplitude here. It's quite clear that the mean is 0, but it varies, okay. What you can do is you can plug that through the computer to get the Fourier transform, and you get a signal that looks like this. You've got a bit of noise, okay, but you can see quite clearly there's a peak here at 13, 26, 39, and 60 hertz. And so that's the fundamental frequency. That's be the second harmonic and the third harmonic, okay, and then that will be due to the mains supply that's being used, okay. But you can see quite clearly that you don't want to excite your system at 13 hertz. Because you get this massive peak in frequency, and that's your fundamental. So that's chapters 2 to 4, okay, and that's all to do with single degree of freedom systems and some basics of forcing functions and how we deal with them, how we solve those sorts of systems.